Welcome back. In this lecture, we will look at some aspects of an electric vehicle powered via a battery. There are three important features when we consider a battery for electric vehicle. The energy capacity that can be provided by the battery is critical. The power that can be delivered by a battery is important. And you should also be able to estimate the life of a battery. So while these two can be more quantitatively assessed, this is rather hard. However, we'll provide an approximate way of assessing the life of a battery. All these three quantities depend critically on the voltage provided by the battery, which is not a constant and may vary. The nominal or the average voltage is indicated here, but the battery during the operation may have a voltage above the nominal voltage. It can be a certain maximum voltage, or the voltage can fall below the nominal voltage to a certain minimum voltage. So the operational value of the voltage can vary. Energy is required to overcome friction against the road, the drag against the ambient atmosphere, also the drive train losses. We have clarified this when we, in an earlier lecture, introducing electric vehicles. So, as a general thumb rule, it is possible to travel about 6 kilometers in a typical electric vehicle when you use 1 kilowatt hour of energy. So, per unit of this, you are able to travel 6 kilometers. So, the capacity, energy capacity, scales as the active mass of the electrode of the battery. So if you want to increase the capacity, you have to increase the mass of active material. That would also increase the weight of the battery involved. Also, it is the energy that can be delivered by a battery is critically dependent on the SOC window you are going to be operating the battery. If you SOC means state of charge. If you discharge the battery to a greater extent, you may be able to get more energy from the battery, but the greater, if you are going to discharge to a greater extent, the cycle life of the battery is going to be decreased. So it is the trade-off. If you use, if you discharge to a smaller SOC, let's say 50%, or 70% SOC, then you may be able to get lesser energy out of the battery, but you may be able to have the battery for more cycles. However, if you go to, let's say, you're able to discharge 80% of the battery, of course, you are going to get more energy from the battery, but the number of times you can discharge and charge the battery will be lesser. So this trade-off depends upon the battery chemistry and other considerations. The power of required for the vehicle from the battery depends critically on the velocity of the vehicle. And in some cases, if the vehicle is climbing over an inclination, then the slope of the climb critically determines the power requirement. So a good thumb rule is a typical requirement of power is about 50 kilowatts. This is not a small number. So this is a reasonably big number. So a battery pack that is able to provide 50 kilowatt is reasonably heavy. So you're ohmically limited. So the voltage from a battery is given by, can be approximated as VOCV minus I R omega. This is the ohmic resistance. In an earlier lecture, for example, in this lecture, we had determined how to estimate the maximum power from a fuel cell, but the concepts are fairly similar. Even in a fuel cell, you use this kind of formula to represent the voltage that you can get. It is possible to get quantitatively, just a simple math. Power is V times I. You differentiate with respect to I to get the maxima in power. So the maximum power is given by square of VOCV divided by 4R omega. So if you want to increase the maximum power, you have to decrease R omega. One way to do that is that increase the separator area. So if you want to increase the maximum power, you have to scale the separator area. You can again estimate the voltage at maximum power. That can be done quantitatively. Please look at this lecture. So that would amount to VOCV divided by 2. However, you do not want to be operating the battery below a certain voltage. So if VOCV by 2 is less than a particular value, you do not go to that value, but you restrict the voltage to some cutoff, V cutoff. You do not go below a certain cutoff potential. If the V cutoff is greater than this number, the power maximum can be is given by this formula, V times I. This is the voltage of operation. This is the current from the battery. So all these things help you to estimate the maximum power that can be obtained from a battery pack. So these concepts, capacity, turnover, and so on, help you estimate the lifetime of a battery. This is a fairly involved process, depends upon a variety of detailed conditions of operation, but we provide an approximate way of how to think about the life of a battery. The degradation of a battery is approximately proportional to number of coulombs charge passed in a battery. If the more charge has been passed, gradually the battery degrades. And so therefore, a simple heuristic is that degradation is proportional to number of coulombs passed in the battery. So we define a dimensionless number called the capacity turnover. This represents the total amount of charge passed before the battery is degraded completely. What do you mean by that? Supposing you do not typically want to be you do not want to be operating the battery if the battery gives, let's say, less than 80% of the rated capacity. Okay, so let's put that as a mark for when the battery is deemed to be degraded. So before that happens, you may have operated the battery, let's say, over 1,000 cycles. So when you operate the battery over 1,000 cycles, the total amount of charge that has been passed over these 1,000 cycles goes in the numerator, divided by the nominal capacity would give you the capacity turnover. This is a dimensionless quantity. Okay, so this is the total amount of charge that's passed divided by the nominal capacity. So there are intuitive ways of thinking about capacity turnover number. So let's first look at the capacity turnover at a particular voltage. Let's say at this, not a particular voltage, particular temperature as a function of SOC window. Supposing you are discharging the battery completely, that is, you vary the SOC to 100% discharge, that is, you're completely discharging, then the capacity turnover comes down because the degradation is enhanced if you discharge completely. So a way to think about degradation is if you keep the SOC window to a smaller number, then the number of the capacity turnover number is greater. So the degradation is limited if you keep the SOC window to a smaller range. So the more you discharge, again, this is a trade-off. The more you discharge, the capacity that can be obtained is greater. However, the degradation is also enhanced in that when you discharge to a greater extent. In addition, most of the degradation mechanisms are activated processes. So when you increase the temperature, the degradation also is hastened. Therefore, the turnover number also decreases. Therefore, in a country like India, tropical battery itself is an important topic. How do you design batteries for tropical condition where the temperature are reasonably high is an important topic of current research. But the two features that you have to remember is the greater the SOC window of operation, your turnover number decreases. If you increase the temperature, your turnover number decreases. I mean, capacity turnover number decreases. So from this capacity turnover number, you can estimate the cycle life. So cycle life is the number of cycles possible over a battery lifetime. For example, you may want to charge and discharge for between 500 to 1,000 times for a typical battery. So the formula is straightforward. So you can split the cycle life into two quantities. This times this, okay, because in capacity turnover is normalized by nominal capacity. So this times this will give you the total amount of charge that is passed before the battery is degraded. That is given by this times this. That is one way to think. Divided by ampere hour per cycle. That is the amount of charge passed per cycle. Okay. So this quantity divided by this quantity will give you the number of cycles possible over a battery lifetime. So many aspects of the battery is quite desirable, especially the aspect of efficiency, as well as it is not polluting. It doesn't generate carbon dioxide. So despite these features, electric vehicles are not that prevalent because of two main reasons. One is that there is this range anxiety, okay? Because the energy capacity is limited compared to petrol, the distance to which you can travel per single charge is still less. Okay, so you can travel within the city, but if you want to go to a longer distance, it's always challenging. So this range anxiety is an important feature. Cost is still quite expensive. Petrol is hard to beat because it has great energy um, per unit mass, power density, as well as is relatively cheap. So to beat gasoline vehicles, the cost of batteries vehicle has to come down, or the cost of batteries has to come down. If these two issues are met with different kinds of chemistry that are being explored, then battery vehicles will become more prevalent. So in the next lecture, we will look at hybrid vehicle architecture. That's going to be taken up in the as the next topic. Thank you.